All right, let's launch on in and do some components and circuit measurements. And let's turn the clicker on and see if it works better with power. There. This should be a little bit of a repeat for everybody, but again, this has got some good information, and so it's one of those things that it's good to repeat. So if you already knew this, try to hold the yawn to a minimum. Well, we talked about wires already. We talked about, the reason we use copper versus silver and aluminum is just cost. As far as using it against gold, which is a much better conductor, but copper wire is pretty darn expensive, so imagine what gold wire would be. An aluminum wire, as long as we terminate it correctly, is still a pretty good choice, but it got such a bad rap in the 70s that copper has pretty much stayed the king as far as what we use in the electronics field and electrical field. Again, we talked about the wire gauges, standard size based on cross-sectional area. And again, those numbers are often reversed to what we think. Excuse me. The smaller the number, the larger the wire, and the larger the number, the smaller the wire. So it's kind of inversely proportional in that respect. And we call that example 24 gauge, and a 24 gauge wire has a small cross-sectional area. We get into what we use in our homes, 14, 12, 10, and 8. They're larger as far as their cross-sectional area. And then we get into the large wires. You'll hear double aught wire sizes, things like that, even larger than the 0 gauge. So, and of course, the current capacity of the wire increases with the wire size. If I tried to run my stove off of a drop cord, you'd probably see it glow for a minute, and then you'd smell something, and then either the breaker would trip or the wire would burn into, and wouldn't last very long. We would be trying to source too heavy of a current on too small of a wire. So we do want to make sure when we're hooking in something brand new, we're using the correct wire size. Again, there are all sorts of tools out there that will take that into consideration on the web. It'll take the distance you run, the maximum load, the conduit size, the conduit fill, all that into consideration when you're trying to do a wire sizing. And of course, we talked about PCB board traces already. Printed circuit boards typically are copper, and what happens is you begin with a copper plated board. The board is entirely copper plated. There's a coating you put on that will literally allow the rest of it to be etched away. So we create traces and runs by eliminating the copper we don't want, keeping the copper we do want. And the one thing that you can run into is what the industry calls an under etch on a board, and that is where some of the etching didn't go completely as planned, and you've got a sliver of copper that, as the board expands and contracts, can sometimes make and short, and that's also one of those things that becomes intermittent with heat being applied to it. Don't see it as much as you used to. They do a better job of catching these things after they manufacture them, but those are one of those nagging things you can find in electronics as well. Again, we talked about it, different insulators, the average breakdown voltage. So we see that the breakdown voltage is much higher as we move from rubber to paper to Teflon to glass. But we typically use a rubber or plastic insulation. We used to test our product out there now in Bradley at 140 degrees Fahrenheit continuously. And one of the things we had to do was the insulation on these wires would dry out with time. And you can buy this Teflon coated wire that's very expensive, but guess what? It holds up to that heat like nobody's business. So we started redoing those racks with Teflon wire, and they're probably still going now, as opposed to about every year and a half. You had to bring those things in and do a complete overhaul because they stayed 140 degrees Fahrenheit around the clock as they were testing product. So Teflon does make a good insulator. We talked about resistors, and I'm just gonna pass something around. Let me grab it real quick. Resistors come in all shapes and sizes. I'll pass this around. You'll see just how small, and they're even smaller than what's on that paper now. Of course, when we change their size, we also change their ampacity. So obviously, our larger resistor, like you see on this board, would have a higher wattage or a higher ampacity than these guys that are being passed around. If you look at those very small ones, it's impossible to almost see them, much less read a value on them.
Nice.
But that's what allows us to have such small components in the electronics industry.
What wattage are the tiny ones?
Hmm?
What wattage are the tiny ones?
Probably measured in the milliwatts, very small wattage.
Yeah.
So you're talking about something that's not able to handle a large current
Yeah, like what's in your
value.
phone?
And that was from 10 years ago. So, but it's much smaller than that, and you really kind of hit a point in diminishing returns where they can't handle any current at all, or virtually no current.
Most IC chips have ingrained in their circuitry resistors, and they're so small you need a microscope to see them.
Well, those very smallest ones there aren't far from me there. Magnification helps, but when you have to rub your finger on the board to make sure there's really something on the pads.
Yeah.
Carbon copper says it's the most common type. I don't know, that may still be true because of the consumer industry. Some of these resistors that's on this board are carbon comp. And the consumer industry, you know, the tolerances can usually be very wide. Carbon comps, by their very nature, soak up and give off a lot of water as humidity changes. They're very low cost, but they're not very accurate at all. Maybe up into the 20% range, depending on just how cheap it's done. So again, it's just metal leads inserted in some carbon, and because there is no wire wound or any kind of thing that gets us close to being a fixed resistor, it does vary quite a bit. But other types are wire wound metal films, and in addition to the carbon comp. The metal films usually have a little more of a reverse, or excuse me, an hourglass shape. They're bigger and then thin up a little bit on the inside and then get bigger at the bottom. And but those are a little more accurate. They're a little more well made, and they handle temperature a little more. And there's the difference. These are your metal films, and you notice kind of the hourglass shape to it. That's a wire wound. And what literally happens with this top guy is there's actually a wire, a resistive wire in there, and we can determine with precision a little more the resistance value because that wire has a fixed resistance per length. So if we want a more carefully valued resistor, we can use those wire wounds. Of course, they cost a little bit, but they're also higher wattage by virtue of what they're doing. You'll typically see those sticking up off the board. They're handling so much current, they get pretty darn hot. So if you ever see one of them, you can get your hand near it, but if you touch it, it could potentially burn you. It can get that hot. So they're kind of a load resistor type thing. And these integrated resistors, what you got here is just what you see. You got a common pin. So let's say this was, you need a case where you need 8 10K resistors or even 6 10K resistors that you got to populate a board with. Well, if you look, here's a common pin that goes to one side of all these resistors. And if I measured from that common pin to here, I'd measure 10K here, 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 and here. So what that does in the electronics world, particularly the electronics consumer world and even the industrial world, so it allows us to put in one component that becomes 8 different resistors for us without having to populate that board with 8 independent resistors and take a chance on something happening. So, and it can go this way too, they can go straight across without the common pin, so it kind of depends upon your application as to whether, they call those SIPs, that's single inline package. And we call a lot of ICs DIPs, which stands for dual inline package. So a SIP typically only has legs on one side, whereas this DIP would have, dual inline package would have legs on both sides. And you're already seeing how tiny these guys are. And a lot of times you can read, it's amazing how good they've got at screening these values on these resistors, like this 122 that you see here. That's 12 with 2 zeros, just like we'd read the color code. So that would be a 1200 ohm resistor, or 1.2K. So we have gotten it even to where, even on some of the tiniest tiny resistors, we can still have the value screened on them or sprayed on them. I'd say 5% is the most common. There are a few 2% out there, but 5 by and large rules the industry. And even in consumer electronics, some of the cheaper stuff, you'll see 10 and 20%. But medical devices, things that fly, astronauts to the moon, they're gonna have these less than 2% tolerances. A lot more precision, because if I'm trying to hit a target that's hundreds of thousands of miles away, I need something that's pretty dead on. Not a lot of room for error in that kind of system. So you'll see something as low as even 0.001%, that's small. Already talked about color code, band 1, band 2, band 3, and band 4. What you have is band 1 would be the first number you would write down. So for instance, a 2.7K, we have a 2.7K ohm resistor at 10%. We would go down and we'd figure out that 2 would be red, 7 would be violet, and then it's the number of zeros after the 2 and the 7. So to get the 2.7K, we have to write 2 zeros. So we'd see red again. And if it's 10%, what's our color coded band, our fourth band? See who remembers.
Gold, silver,
Silver. Silver is 10, gold is 5. So if it were 5% instead of silver, it would be gold. So band 1 is what we write down. So let's figure this one out. What is red? 2. What is violet?
7.
And what is black? 0. So how many zeros will I put?
3 zeros.
I'll put 0 zeros. Remember, the third band is the number of zeros. So if it's brown, I would put 1. If it's red, I would put 2, and so forth and so on. But the third band is 0 zeros. So it's a 27 ohm, and it's gold, so what's my tolerance? 5%. So this particular one would be a 27 ohm, 5% resistor. How many of you remember the mnemonic for color code? Bad boys race our young girls, but violet generally wins. Almost incorporated the Old Navy one there for a second.
What's the old name one?
So, be careful with that one. Bad boys race our young girls, but violet generally wins. All right, so there it is in black and white. Color code if you need it. You can always leave it up. All right, there are some alphanumeric codes. I could put on my hand the number of times I've seen an alphanumeric code on a resistor. Y'all want to see how many times I've seen it? None. It's like It's like Sasquatch, I guess, it exists, but I had never seen it. And I worked in the industry for about near 30 years. So apparently somebody out there somewhere is using alphanumeric codes on resistors, but I have never seen one. So if I ever encountered it, I would have to look it up. I would encourage you to do the same, because no need in learning something that you'll never potentially realize. So the size of the resistor is usually indicative of how much power. The larger the resistor, and I was going to bring some down, I'll try to grab something there to break and show you the difference in sizing there. We've had some potentiometers in here. We'll probably get some more at some point too. But a potentiometer is nothing but a variable resistor. We talked about it already, the old-fashioned TVs where you turn the volume up and down. When you turn it all the way down, the resistance is very high or low. If you turn the volume all the way down, are you increasing the resistance or decreasing the resistance?
No, you turn it all the way down, and you said you decrease the resistance,
I'm asking, do you decrease it or increase it when you turn your volume down?
you increase it.
Decrease it. I mean increase it, sorry. So that back. It's Monday morning and I have a head cold, so I'm sorry.
When you turn it up, you let it flow
Yeah, you're
through.
lowering the resistance and therefore you're getting more current flow and you're getting higher volume. So that's potentiometer. That's something you use every day. Right before your very eyes, if you have still one of the old-fashioned stereos. Now mine's got the little button that you push up and down that I hate so dearly, because when you used to, we drove up to a window, you could turn it down real quick, and now you have to, bring it on down. But again, all this is, we talked about wire wound resistors. All a potentiometer is a wire wound resistor. There is a wire that is laid in a semicircle, almost a full circle, all the way between the A circle and the B circle, the A circle and the C circle, I should say. And that wire determines the resistance. So it's laid out a lot more neatly. It's laid out kind of like sticks in a row, but they're interconnected. But it goes all the way around, almost 270 degrees typically, that resistor. So if I measure from A to C, I'm going to measure the full value of that potentiometer. And that's because this is basically this right here. Here's A, here is C, and I've got wire that does kind of like this all the way between them. So if this were a 100 ohm wire, if I measure from A to C, I'm going to measure 100 ohms, always, or something very close. I mean, it's not always going to be dead on 100 ohms. It might be 99.8 or 101.2. So that's what I'm going to measure. Now the middle leg is what we call a wiper. And this wiper is usually designated by an arrow, and it actually touches this resistor somehow. Well, not somehow, it's laying on top of it. It's just it's a metal tab that literally just rubs back and forth on that resistor, just like that. And as we dial that potentiometer, it's moving across that resistor. So if this were 100 ohm and I had it set dead center, I'm going to read 50 ohms. And I'm going to read 50 ohms, this is B. I'm going to read 50 ohms from A to B and from B to C, because I'm literally dead center of that pipe, or somewhere close. And again, we're talking nominal values, because 100 typically isn't always exactly 100. But if I change the location of B by dialing it different, and when I show this error, I'm actually talking about this wiper coming in this semicircle, but I'm drawing it out flat. But if I change B to right here, and that's about 25% across, what am I going to measure from A to B if I'm about a quarter of the way down? 25 ohms. What am I gonna measure from B to C? About 75 ohms. So it just depends on, one, where I'm dialing across this potentiometer and where I'm tapping on that potentiometer. I can tap either between A and C or B and C and get a variable resistance, but it's going to vary differently. If I go A to B and I start here and I've got my potentiometer right here, I'm going to measure about 0 ohms, and it's going to get increasingly larger going that way. But if I measure from B to C and I'm right here all the way down, I'm going to measure the full value, and then it's going to get lower and lower as I dial it. So it all just depends on which side of my tap that I'm reading from of what I'll get. So all a potentiometer is a variable resistor. They make a linear type and they make a non-linear type. We already talked about that. If on that 100 ohm, I had 0 ohms and 100 ohms. As I dial it, it's going to go from 0 to 100 at a linear type scale. But audio pots tend to do more like this. They tend to rise slowly and then gain right there a light at the end. And the reason for that is we want some, on a pot for audio, we want to be able to set that exact volume. Not too hard, not too loud, not too quiet, but somewhere just right. And this shouldn't have went down. It should look more like that. But that gives us the ability to dial in an exact volume, unless we just crank it up and just fully do it. And then as we get toward that last 25%, it usually shoots up quite a bit. But that's the difference between a linear and a non-linear. And if you replace one, make sure you're replacing it with the right type, or the behavior of that potentiometer, or at least whatever it's on, is going to change. Typically, you'll see it stamped. The outside of it is either plastic or metal. It'll either be sprayed on if it's plastic, or stamped if it's metal. And it could be printed exactly 5K, just as you see right there, or it may be 502 like a resistor. 99% of the time, probably 100% of the time, you'll see that. It's just too easy to put the exact value when you're doing a stamp. And again, these resistors, potentiometers come in different applications. This is typically going to be, whoops, you can't touch the board. This is typically going to be inside of a piece of equipment that you're not dialing. That potentiometer is more for a calibration setting than a user interface, simply because it won't cotton to too many turns. You get twisting on them and dialing on them very much. After so many, they just can't handle it. They give up the ghost, so to speak. And you just have to replace it at that point. But if it's inside where a calibration person comes in, they're going to have what we call a pot tweaker, a small device used on those, and they're going to have to know how to set it. And typically, they'll seal it with this stuff called torque seal. But again, it's not a user type application, it's more for inside the calibration or setting. Now, when we had some universal conveyors, they had some potentiometers that looked like this, and that would determine the conveyor speed, and we could change that potentiometer to change the conveyor speed. They're a little more robust than these guys here. And of course, these are the ones that you see that are meant to be dialed upon over and over and over. They're a lot more robust. They're made to be utilized over and over and over again. And that's the symbol. You're going to see a wiper. That means you can vary it. Rheostats are used in AC. We'll probably get to talk about them a little later. Other variable resistors, metal oxide resistors, change in resistance in response to a change in voltage. Thermistors change in resistance in response to a change in temperature, and photoconductive. these little eyes. I remember my brother had one of those little things that you screw a light bulb in, and it would detect when it got dark, and the light would come on when it got dark at his house. And his car was there one day, and I went to his house and, you know, knocked on the door, and like a minute and a half after I knocked on his door, because I knew he was home, his car was there, the light came on. So I stood there, waited. It was kind of dusk, it wasn't full dark yet, and light went off. I thought, well, you rude rascal. You know, come and check, see who it is. And so I knocked on the door again. About 10, 15 seconds later, the light came back on. You gonna open, I even said, you gonna open the door or not, you know? And stood there a few more seconds and light went off. I said, well, bump this, I'm gonna walk to the car, you know. About the time I walked to the car, light went off, and I said, you know, then I'm getting in the car, the light came back on. It was right in the early stage of, he wasn't home, early stage of detecting, and it would get enough light to, or enough dark to set it off, and then I guess it would see its own light being inside of a white porch, and it would cut itself off after a little bit of time. But I talked bad about my brother that day. But yeah, these little photos are just that. We talked about batteries. A component converts chemical, thermal, or light energy to electrical energy, and produces a difference of potential across its terminals. Who's checked the 9-volt batteries using their tongue? I've done it. I don't do it recently, but I've done it. And your tongue can read that difference of potential. I can set my finger across it. I can even lick my finger and put it across it, and I won't feel a tingle. But you pop that 9-volt battery on your tongue, and it'll rattle you a little bit. Not a good recommended way to do it, but that's that difference of potential that we see there. A cell, which we talk about inside of a battery, is a unit designed to produce electrical energy through thermal, heat, chemical, or optical means. So it's just chemicals inside of, like our car battery, they produce a difference in voltage across the terminals. Mentioned to you before, and I'm going to find a dead 9-volt battery and bring it in here. We'll take a pair of cutters and cut it apart. But a cell is 1.5 volts. And inside of a little 9-volt battery are 6 1.5-volt cells, prettiest you ever seen. And they're just shy of being AAA size, a little bit short. You can't quite put them in. I thought one day I'll just get some AAA batteries out of here, but they're just a little bit smaller than a AAA. And again, if we stack those 6 cells in series, our voltage adds. So if we take 6 1.5 volts, and we're going positive to negative, positive to negative, positive to negative, and we're stacking them, and that's how we get a 9-volt battery. And when we take that battery apart, I say I'll try to go find one in a little bit. You'll actually see there's a little pad on each end of that battery that actually series these cells together inside that 9-volt. Of course, capacity is how long the battery will last. If you go to Walmart or AutoZone or anything else, you can find a company out there that has a much higher capacity battery called Optima. And of course, you pay about 3 times what you do for a regular battery for them. But they do have a much higher capacity. A lot of boats use them for trolling motors and such.
Cycle.
If a battery has a 1 amp hour rating, then theoretically it should be able to give off 1 amp for an hour, or half an amp for 2 hours, or a quarter of an amp for 4 hours, whatever the case may be. And that's a theoretical. And most of your lead acid batteries, they don't like to be fully discharged. Alkalines, they're meant to be used until they're gone. But you do that continually to a lead acid battery like you have in your car, you're going to shorten the life of that battery just by fully discharging it. And again, they come in all shapes and sizes. I'll have to say that the nickel metal hydride and lithium ions, which are the newer ones, don't seem to have as much trouble with the memory problems that they used to have. What would happen on the old batteries is, you know, they start forming what they call a memory, and you have a battery that used to last 4 hours that suddenly won't last but 2 hours, and then after that might last 30 minutes, and then after that might last 15, before you know it. About the time you unplug your laptop good, carry it to the living room and sit down with it saying, I need power. And, those batteries at that point, it's time to replace them. It's called battery memory. It's called memory. It's basically the cells are developing some kind of memory. There's all kind of things on the web about how you can get rid of that memory. I won't go into some of those because some of them could cause the battery to explode in your face. But I've not seen a lot of success. Maybe I'm just doing it wrong.
What called?
It's just time. Just time. The chemicals inside of those develop what they call memory, more or less.
Is that why my laptop battery's got amnesia?
That could be it. I'm sorry, what was the question? See what I did?
If you, leave a laptop plugged in for.
Yeah, it'll kill
time
it.
and just keep it for days on end, would it develop that memory like
It
that?
particularly would with the whole NICAD stuff. I don't see it as much with the lithium ion. But like I've got one I dedicate. I try to remember to unplug it every once in a while just to do that. But every time I've unplugged it lately, it's held.
Biggest thing that kills your lithium ions is running them completely dead. They don't like
Don't
that.
like it either.
Yeah, I've done that to mine. It's an ion, and it I at one point I wasn't taking it out of the house. I was just leaving it plugged into the TV, and I just used my TV as the big monitor. And I tried to unplug it and take it, bring it up here to school. Battery lasted all of 15 minutes.
And all of them will eventually age. And the good thing is, that's the one, I'm a non-OEM guy when it comes to certain things. If I can find something else that'll work, that's not standard equipment. But laptop batteries and camera batteries, I'm pretty particular about those because I've bought some cheap stuff that you can get on eBay and Amazon. That's one of the things, in my opinion, you get what you pay for. Yeah. So I try to replace a laptop battery with a genuine, and even then you have to watch it because eBay is slammed full of rip-offs in that respect. So you're finding that if everybody else is selling it for $30 and some guy's got it for $7.50 and it says HP genuine on it, it probably ain't HP genuine.
It's a genuine something, all right.
So somebody got a hold of the labels or managed to copy it. I bought a jack one time and it had what looked like the little Michelin man on it. Bought it at Sky City up in Cornelia. And I was bragging because I didn't pay much for this hydraulic jack. And it had Michelin on it. And I thought, man, I can't believe it. And it was about 6 months after I looked at it. And it was Michelin, no E. I thought, wait a minute, Michelin is spelled Michelin. Oh, crap, I've been ripped off. But it worked, but it was not a true Michelin jack. We talked about if we connect batteries in series, we increase the voltage. We do not increase the capacity. If this is an 80 milliamp battery and this is an 80 milliamp battery and they're 1.5 volts, we're going to get 3 volts at 80 milliamps. Capacity has not increased by putting them in series, whatever the capacity is of the single battery. So will the capacity be of the stacked series batteries. However, if we parallel them, and again, here we're putting negative, here's positive, that goes to the negative of this one, here's positive. We're stacking negative to positive, and we're keeping the same capacity. But when we parallel, we're going positive to positive and negative to negative. We're keeping the voltage. Voltage remains the same. We are doubling the capacity at that point. So that's why you see, if anybody's ever seen a solar setup where you got batteries that you're charging with solar, these things connected in parallel, or at least some portions of them. That's because you're sourcing the same voltage to them, but you're trying to increase your capacity. Remember hearing a story about a guy that had got his home battery backed up down there in Florida, and they make these inverters that can switch your home, and what it is there's certain loads in your house that become critical loads, and if the grid goes off power, this inverter will only only source to the certain portions of your house you designated as critical, such as freezers, refrigerators, potentially AC units, if that's what you want, a pump if you're living out in the country where you don't have city water pumping to you. Well, anyway, this guy's power went out. He called SMA, which is one of the leading inverter manufacturers in the world, and he told them, said, look, he said, power went out, battery backup went on, and he said, but I had power for like 5 minutes, and I'm dead. So SMA is pretty, they're pretty good in the industry. They sent a tech over right away, and whoever had installed this had installed 2 batteries, and that was it. 2 regular lead acid batteries. Just to give you a little bit of idea of how long the lead acid battery will last, we were without power in Statesboro over the weekend before last after the hurricane. So I hooked up an inverter to my car and kept my wife's van parked in front of it just in case the battery fully died. That inverter was able to power a fan, about a 12-inch fan on a stand for about 4 hours at low speed. So you can imagine how long that lasted in his home. So bottom line, the installer didn't do any kind of capacity check. He just got the system quote unquote operational, took his check and walked away. But yeah, we have to have, if we're drawing a large capacity, we have to have lots of batteries. When you start talking about battery backing up your home, you're gonna have a room, probably a bedroom sized room, dedicated to having batteries. It's got to be ventilated because they outsource gases that can explode. That's the only thing that's kept solar power is from really running off the charts is the lack of being able to run at night and have some sort of place you could draw. If you could buy a battery that would literally power your house all night long until the next day for $1,000 or $1,500, we'd all have solar on our houses right now. But,
Does the solar get off the gas like the other batteries?
well, they make some sealed batteries that are a little safer, but they're like 3 times what lead acid is. So, I mean, just imagine having to pay $300 for a battery and having to have, I don't know, 40 or 50 of those. It gets a little expensive when you start talking those kind of numbers. And then if you were to have 3 or 4 days of sustained, dense cloudiness, not being able to recharge, I would, if I were gonna go solar, I'd put solar on my roof and I'd have a backup generator. If I wanted some kind of way to
Backup generator?
Yeah.
Alright.
Until this breakthrough in batteries that they keep talking about.
What's up, the zero gravity technology they're talking about? Have you heard anything about that?
I've heard about it a little bit.
Yeah,
What's that one?
Kinda still fuzzy,
Yeah.
I don't wanna talk enough facts.
Yeah, show me the actual device. I mean, I've been hearing since the 80s. I don't know if anybody remembers the little square cars that were electric that came out in the 80s. Man, there were article after article in the 80s now. Some of y'all weren't even born in the 80s, revolutionary battery technology that will break through the industry. The 90s have come, the 2000s, and almost the 2010s have gone, and I've yet to see an amazing breakthrough in battery. We've progressively improved it, but we hadn't gotten major. Of course, DC power supplies. DC power supplies, if you're a troubleshooting technician, this is a good thing to have on your bench. It allows you to do several things. We can vary the power out of these DC supplies, so we can have anywhere from 0 to, a lot of them go 25, 30, some of them go up to 120 volts DC. And the other thing we can do is we can limit the current. If we're checking something out and we know it's not supposed to draw more than 100 milliamps, if it's got a current limiting amount, we can minimize the amount of current it can output, which means when we're trying to fix something, we don't burn it up by allowing too much current to flow through that circuit. So this is one of those things that it's good to have around or available to you in some shape or form. And they run from, if you buy a cheaper version made in the Asia Pacific area, $20, $30 all the way up to you go out and buy a nice high-end Lambda supply, you can spend several $100s. So it all depends on where you can put your money, and everywhere in between those two.
And, another
only done for a power supply, that's like the big block on the
Holy crap,
charger.
3 volts.
Yeah, so this one we can vary.
Yeah.
Yeah, and just like those chargers come in different current values, you know, these little switching, chargers that you get for charging cell phones, some of them are not much bigger than my thumb, but a little bit thicker. And then you look on your, some of your HP printers and laptops are much larger blocks, and obviously those are sourcing higher current is what they're doing, but they're typically fixed. Whereas the variable allows us to manipulate the voltage and or current depending on the supply. And again, this is a varying output. The arrow, again, just like it represented a varying output on a resistor, represents a varying output for a power supply. And then just more pictures of that. When we talk about negative voltages, sometimes we're talking in respect to, for instance, here is V. Side A is positive with respect to side B, and side B is negative with respect to side A. Which means if we come in here with a multimeter and we place our red lead here, and we're reading volts, and we place our black lead here, and this is a 9-volt supply, what's going to be on our meter? 9 volts, or somewhere thereabouts, because again, we're not going to see exact. But what happens if we swap those leads? What if we put our red lead to our negative, and our black lead to our positive? What are we going to read on our meter? Negative 9. That's because with respect to what's positive and negative, we have our leads switched. We have our positive lead on the negative side, our negative lead on the positive side, and we're going to read what to the meter says it's a negative voltage, but it has to do with the orientation of our meter. We can go out to our car batteries right now and hook up a meter, and if we go red to red, black to black, we'll get 13 volts. If we go red to black and black to red, we'll get a negative 13 or somewhere in that ballpark. All right, and here is the bane of the electronics industry that I try to drive in everybody's head. When a switch is working, it is closed, and when a switch is not working, and that's really a bad terminology, let's drop back. When a switch completes the circuit, it's closed. When it breaks the circuit, it's open. So that's the difference between open and closed. That's not too hard when we think about a gate. Open gate, closed gate, open gate, closed gate. Where it gets hard, and this is really where I was referring to, is we talked about that lamp already. I got that lamp sitting on my desk that starts winking on and off. And I go up there and wall up that desk, and that lamp comes back on. The world says, that lamp's got a short in it. If that lamp had a short in it, you'd be smelling smoke or tripping a breaker. And you sure wouldn't want to beat on the desk because you don't want to bring a short back. You want to find that short and get rid of it. That lamp has an open in it, and that's what's happening is we've got a light bulb out here. It looks like this. It's going back to our lamp. One side is going to both sides are going to our AC outlet and plugged in. Well, what happens is, usually somewhere around here, we've got a loose wire on a screw, and when we bang on that thing, we're making that, closing that circuit, or making that open go away. So it doesn't have a short in it. My air conditioner had a short in it. We just bought a mobile home this weekend, and won't go into a lot of details, but we probably did something we shouldn't have, and all of a sudden, about 5 minutes after we did what we'd done, I smelled something burning, and I'm like, and Tracy was running a vacuum, and I said, ooh, I hope it ain't that vacuum. Well, I got closer to the air conditioner, and I had to pull the bottom panel off. There was a wire on fire in there.
Oh my God.
So something shorted, and that wire was drawing way more current than it can handle, and what happened was the insulation got on fire. So we had this nice, fresh, clean smelling place that we just spent, I don't know, about 4 hours, road doctoring and so forth. And the acrid smell of insulation burning came into play. And I don't mind working on certain things, but an air conditioner isn't one of them. But I got a good friend that works on it. He's coming to look at it. But we turned the power off and just forgot about it for a little while. But remember, closed means we've got the switch actuated inside the circuit. Open means we open that switch. And don't forget the difference between a short and an open. An open means we have broken the circuit. A short means something has shorted together that shouldn't have typically. All right, I thought we'd make it, but we're not. So we got about 11 more slides to go. Let's take a break till about 9 o'clock. We'll come back and we'll finish this up. I'm gonna go get some resistors. And,
I got a burger.
did you pause the video? It's got a little terminal in the middle and some exposed wires back here. We can actually slide this little centerpiece up and down, and it's like a potentiometer. We can vary the resistance between the two. So let's see if it tells how many watts. I don't see a wattage on this one. How about this guy? It's 50 ohms, 100 watt. And this one is 10 ohms, 25 watt. So I'll just, I'll start them on this end. And obviously you'll see that that's the other end of the spectrum from those two tiny ones you saw on the paper there. Double pole, double throw toggle switches. Wow. Okay.
I'm watching the perpetual cat.
Oh, awesome. What happens with a single switch is, and this is just like a single switch is just like our light switches. We break the hot wire, which is L1 typically, and it's going out here to our bulb, and the neutral is already fed in from the other end. So what happens is when we close that switch, we're feeding power to our bulb up here. That's what we call a single pole, single throw. That means there's only one pole that we're breaking, and there's only one throw direction that's either open or closed, and that's what powers our lamp. But they make a double pole, double throw switch, and it works just like a single pole. Actually, this is a double pole, single throw, except two connections move at the same time. So what happens is we can double the amount of current we could run just by having this, or there may be more than one thing that we want to power. I used to use one like this to control the lights and siren back when I was a volunteer fireman. And you know, you're gonna find all kind of creative ways to do stuff back then. But then at one point I got to where I wanted to run with just my lights without my siren, so I ended up changing it. But this lets me connect two things at one time with just the throw of a single switch. Get this down. This is something you're going to be seeing again and again and again and again. Normally closed switch versus a normally open switch. The switch on the left is normally closed, and if we press it, it opens. So we've got something that we want normally to stay on, and we want to be able to press it and interrupt it. That's a normally closed switch. A normally open switch is just the opposite. It's normally open until we press it, and then it closes. So when we talk about our light switches, they are a normally open switch, and when we turn them on, they close. So a light switch in your home is what you would see on the right. It's a form of that type anyway. It's a normally open switch. There are two different types of switches out there, and they each have unique properties. Rotary switches, again, it allows us to select multiple settings. So if we've got A, B, C, D, or E, how many of you have got a speed switch in your car? Low, medium, a little bit higher, and all the way to high on your fan. That's a rotary switch. It's just varying the speed of your fan. It's just different settings on that switch or different ways that switch is used in the circuit to vary your fan speed. So if you got a high, medium, and low, you got at least 3 points there.
What about on the automatic, like for temperature? I can set my temperature and it stays that temperature, which, can you use that also?
Not typically, it's gonna be some kind of, closed loop, circuit that's getting feedback, and, it's gonna be computer controlled. You're gonna take out the more, what's the word, analog type features and get more into a digital, and it's gonna be, a closed loop type circuit at that point. So, it's just more automated, basically. You know, before, you just kinda keep, it, basically on your old style, that's what we call an open loop. Open loop means, there's no feedback other than you. You know, if it's too cold in my car, I might crank it a little toward the heat, but what I sometimes do is I don't crank it enough, and I have to end up cranking it a little more, or I crank it too far, and then I have to back it back down, because I went from all of a sudden cold to all of a sudden warm. And my car this morning was a perfect example. It was a little cool, even running just the vent this morning, so I cranked it toward the heat, and then about 15 minutes after I did that, it started getting a little muggy and airish in the car, so I cut it back down a little bit. But with that, obviously, it's getting its own feedback, and it's adapting the temperature based off of a preset point that you set at that point. So I'm not having to guess at where 70 degrees is. I'm telling it 70 degrees. These are dual inline package switches, and these can be set individually. If you take a look right here, we've got 1, 2, 3, 4, 5, 6, 7, 8 independent switches. They each have an on and an off setting. And again, I can control 8 different devices or 8 different settings by putting this switch in. So again, I can drop that in. And a lot of your, I was working on a ceiling fan at the house, and it had the people that moved out, some dastardly individual, and I said dastardly with a D, just in case there's any clarification on the video.
Did he just cut?
Took the remote. And I said, surely there's a way to turn on this fan without the remote. So I go on the web and said, how do you turn on a Hunter fan without the remote? Somebody said, buy a new remote. And got to looking, and sure enough, if that remote's gone, so is your ability to operate the fan.
And the remote costs about half as much as the
Yeah, the
fan.
remote was $40.
Yeah.
And it's in my stepson's room, and Tracy said, what are you gonna
They've
do?
got that kind of switch in them.
Yeah, I said, I'm gonna take that out. So I paid $40 for no remote. They can get up and turn it up and down just like we can.
I put 2 in, and I turned the ceiling fan on in the living room, and the other living room, the fan came on too.
Oh, nice.
So you
They're
have to
coded.
get up there and change the code.
That's right. And that's where I was leading to. These, like you said, these are codes. And you can set each one to have its own unique code where you don't ultimately control the wrong fan, you know, so if they're both set to, you know, all off or something, you're going, if it's in range, you're going to control both fans at the same time. It's kind of like my stepsister and her husband did one time. They had one of them electric blankets that was, each had separate controls, and they swapped them during the night when they were made up the bed the last time. They ended up swapping the 2 controls. He's like me, he's a little hot natured, and she's cold natured. She kept cranking hers up, and he kept cranking his down. He was about to burn up, and she was about to freeze. And they finally figured about 2 o'clock in the morning they had one of those controls. So, but yeah, these switches can be used for a variety of reasons, simply on and off, or like you said, to set a code in a fan, and that's where we see dip switches a lot of times are for setting on devices. Fuses are one-time devices. They're designed to open if it exceeds current, and a fuse is a protective device. Whenever you make a circuit, you want some kind of protective device in there that will blow before wires start melting, blow or trip, and a fuse is supposed to do that. So if you got that 5-amp fuse and all you can find is the cabinet is a 10-amp, you may very well have a fire or at least a melted insulation. So you can go down if you got a 5 and you only got a 4. Doesn't hurt to try the 4. It may blow it just because it may be pulling 4.5 amps and may eventually blow that 4. But you certainly don't want to ever go up in value as far as those fuses, or there can be trouble. And there's your schematic symbols. You see the little wavy line or the little straight line with block around it, that just represents a fuse. Fuse ratings, current, the maximum allowable fuse current before it blows, and the voltage is the voltage across an open fuse that will cause the air in the fuse to ionize and allow the open fuse to conduct. And that's important. If you use the wrong voltage fuse, it can actually arc gap across that fuse and still continue to conduct. So make sure you're replacing the right style fuse with the right style fuse. There are high speed, normal speed, and time delay. The reason we have time delay fuses, what happens to your lights when you first crank your refrigerator, when your refrigerator first cranks up, compressor or your air compressor turns on? They dim a little bit. You get an inrush of current running to that device, and if it had a fast blow fuse in it, it would blow every time because it is exceeding the normal capacity or normal amperage of that device for a very quick second. But if we put a time delay, it allows for that little inrush, and then if it doesn't sustain, we don't blow a fuse. But again, if you put the wrong style fuse in there, if you put a fast blow, it's going to blow it every time. When you replace a fuse, they make these no-touch fuses. They make these little fuse holders that you're supposed to be able to pop them out, and there's supposed to be no current there, no voltage there. There's voltage and current as far as I'm concerned. I don't like this thing. I want power off. I hadn't been killed yet. I'm planning on trying to retain that record. But make sure all power is removed. Only replace the fuse with the same current rating. Only replace it with the same voltage rating, and never replace a fuse with a higher current rating. Anybody remember the old screw-in type fuse? They used to have what they called a Lincoln fuse. Anybody know what that was? Where you put a penny behind them and keep them going.
Never use a penny, have used tinfoil for something.
Don't do that. And there's a story on the internet, I don't know if it's true, but it would keep me from ever doing it anyway, about the, remember the old glass top fuses in your car? Somebody said they had one blow on their windshield wipers one time and replaced it with a 22 shell. And it got hot enough, it fired that shell off. I kind of think that's a cute internet story, but I won't ever put a bullet in a glass top fuse, especially in the car anyway. So fuses, just like their resistor and other counterparts, come in different shapes and sizes. They can be very small and very large. Circuit breakers are typically what we have in our homes. They're not destroyed. The only way to check a fuse is to blow it. And if you've blown it, then it's no longer any good. It's like a flash bulb or like a match. It worked one time. And after that, it won't ever work again. But breakers are resettable. And we got ground fault interrupts, which is a special case. And what ground faults do is they detect a minor change in current from one leg to the other. And what is supposed to happen if I plug in a device like a hairdryer or something like that, is I should have current running from one conductor, the same amount of current running from one conductor to another. But if I become part of that path, one of those conductors may for a moment have higher current than the other, and this ground fault is supposed to kick in and trip out. That's one of the nice breakthroughs we've had. Of course, they can be a little problematic from time to time. They can hiccup a little bit and blow or trip, but at least you can go over and reset it and get it rocking and rolling. And then they've got these arc fault things out there that I want to understand sort of work. The industry, I actually read an article on this arc fault stuff. They said the industry said, we want arc fault, it doesn't exist, so the only way we're ever going to get it is to require it. Okay. So, I don't know if I believe the article, but it made for a good story. Multimeters, you're going to get your hands on some of those here before the day's over. We can read a variety of things, the major four being current, voltage, resistance, and a multimeter can do all three of those. They do make specific meters. They do make just a voltmeter that won't do anything else. They're rare. They do make some amp meters that'll read just current and won't read anything else. They're usually specialty, like microamp meters or something like that. But generally, what you're gonna have and what we'll have are what we call a multimeter that can do at least these three and move some. Just like we said before, to read current, we have to break the circuit. If we want to read current, we're gonna have to open that circuit somehow, insert the ammeter. The ammeter then becomes part of that circuit, closing that circuit and allowing us to read current through that circuit, just like a flow meter in a pipe. Now, we already talked about the fact there are clamp-on ammeters that we can do that with too, and you'll see those as well. But particularly in smaller electronics, we're going to be using the break the circuit type way of doing things. Measuring voltage, we can measure straight across the device, whatever the source voltage is. I can leave my car battery hooked up all day long, running everything inside the car, and it running, but I can still measure the voltage on my car. Same way here, all these outlets, several of them are in parallel one another. I can go read the AC voltage on the outlet without having to interrupt anything that's currently powering there. And resistance. I'm going to say this, cannot be measured with power applied to the circuit. If you hook a meter up and measure resistance on a live circuit, you'll see some pretty neat things, and probably smell some pretty neat things too. And you'll go buy a new voltmeter after that, because it will very likely go poof. So if you're measuring resistance, one, you're going to want to remove power from that circuit, and two, typically the only way to accurately measure a resistor is to remove at least one side of the resistor from the circuit, because that resistor is usually in parallel with other resistances, and we're going to find out before long how that plays a part in changing the value of that resistor. But you'll let the smoke out if you try to measure resistance on a power circuit of the potentially the circuit and definitely the voltmeter. Any questions? All right, I have lab 1. I'm going to turn the lights on. If there's any extras of these, please be sure that Callie gathers them back there. And I'm going to let you kind of work alone on that one. Then we'll go through them.